I will talk to you on metrology for radiation protection today. So it's not such a common issue if we think on metrology and radiation protection together, but it is an important issue because radiation protection influence our achievements in medicine, in technological developments, and also on fundamental research. And it is our duty to provide good measures for radiation, and this involves also to provide metrology for ionizing radiation and radiation protection. So what we all know about metrology is to measure is to know. But in case of radiation protection, the question is sometimes different. Without knowing what, where, and how to measure, you know this is a challenge on top of metrology for radiation protection. In the announcement, you might have read that we have an increasing exposure to ionizing radiation worldwide. This is due to the fact that we have medical therapy, nuclear industry, and other technical development that generates new exposure scenarios, and this increases the amount of radiation exposure to a growing number of workers. On the other hand, we have, due to the increasing urbanization and the change of living conditions for the general public and increasement of exposure to natural radioactivity, that is from radon and also from natural occurring radioactive material that is called the norm material, for example, in building. And this is an exposure for all people, that is for the general public. So radiation protection is an issue we should consider. And the first thing is to understand where the exposure is coming from. This is data provided from UNSCEAR in 2008. It's not so easy to find newer data on a worldwide development here. So we have to stick to this validated data from UNSCEAR in the moment, but it gives us a good impression how the exposure is measured in different fields. So we have the natural exposure, which dominates the total average individual dose of roughly 3 millisieverts per year. And we see that the medical application gives an amount of 0.6 millisievert in this. So the natural part is very important and dominant. If you look to the natural part alone, this is dominated by radon, nearly 50%. Then we have also the cosmic rays, mainly secondary cosmic on Earth. We have terrestrial radiation, and we have the radionuclides we eat or drink. So we have ingestion here. So this is the data of exposure. You see, we have a real amount to be taken care in radiation protection, not only for the workers, but for the general public. And this requires that we provide good radiation protection measures, and therefore we need good metrology for this. Metrology in radiation protection has also a long tradition, but the challenges are changing due to our development. And in the scope of this project, we started to summarize some gaps in radiation protection metrology. And in this first part of the talk, I would like to show you the outcome of this discussion. The gaps in radiation protection metrology were summarized in 6 topics. First, missing reference fields, the discussion on radiation protection quantities, the education and training needs, and then we come also to the question of measuring devices for the application in medicine or in industrial applications. Of course, we have to deal with the activity standards and to combine this in form of type testing, harmonization, and national requirements. These were the topics we started to discuss, and I would like to show you the outcome of this discussion, which was happening in the scope of the workshop, Gaps in Radiation Protection Metrology. So I'm really grateful for Stephen to give us the chance to present our results and to give you, as our colleagues in the field of radiation protection, the possibility to contribute to our findings here. So though this web conference is intended to make me the speaker of this talk, I would like to invite all of you to give me and the consortium of the Support BSS project your feedback on our gaps, on our proposal to cover the needs in radiation protection metrology. And also I would like to invite you to be part of this project and its development. So we started with these 6 topics, and as a first important contribution, we received the view of the International Atomic Energy Agency. And this was indeed very helpful, and I'm glad that Paula Turoy was able to contribute to this. She collected the view of a lot of agency colleagues and combined them in her talk. I cannot explain every detail here, but there was one very important observation. We have differences in reference fields and real workplace fields. There is a special concern about the frequent application of pulsed beams. It's quite obvious. If you calibrate a dosimeter in a classical field, it is not certain that it will work correctly under a pulsed field. Another observation, and I think we all share this, is that we have a growing costs in radionuclides. The access to cesium-137 in future requires huge amount of money, and this includes also the cost for the disposal. And another point that was raised by the agency are the simulated workplace neutron fields, which should satisfy the ISO standard 12789, and there we also observed a gap here. When we have a look to the reference fields, as I said, technology changes bring the needs for new fields. They show us new exposure situations. You see here is a picture of good old history. You see the hand in the X-ray field. And if you think about here a patient and medical staff, we are all aware and we provided radiation protection measures for the application of ionizing radiation in medicine. But the exposure situation are changing fast. Working close to the patient in fluoroscopic examinations and the image-guided interventional procedures are rising. So we have an other exposure scenario again. The increased use of pulse radiation fields in medicine, in industry, and in other applications is observed. And this means that staff that is working in pulsed fields normally is equipped with monitoring devices calibrated and tested in classical reference fields. And of course, we should be working on this part. The reference field should correspond to the calibration field. This is not a minor development. If we look to the number of accelerators installed worldwide, we see that their number is rising and the application of pulsed fields is growing. This was presented by Lisette de la Fuente in the workshop, and she also showed this graph about dose per pulse, here in this example at 15 MV with an approximation of 0.3 milligray, and that simply by the dose is variated only by the repetition rate. To solve this issue, to calculate the dose, we also need to use the tool of Monte Carlo simulation. She explained it in this special reference field and made a cross-link to a running project which is under the development with the aim to create a new reference field. This project is supported by the Ministry of Environment from Germany, and if you are interested in the first results, you can contact Hajo Zutz. Another point we discussed in the scope of reference fields are the neutron fields. Neutron metrology is done in a quite small community worldwide. Their facilities are very expensive, and the needs for different fields are high. High neutron energies, high fluxes, high dose rate pulse fields, epithermal fields, realistic reference fields for flight and therapy, these are all gaps to be addressed to generate a link from calibration to application. So here is a collection that Vincent Gressier presented, and here you can see what is available in Europe in the moment. And clearly, there is no high energy field available above 35 MeV. So in the moment, we have a collaboration with South Africa for that. But you observe here in the collection, the world of neutron metrology is quite small. And we have big gaps in there. For example, the epithermal reference fields. And if you have a look to the response of devices in the area of epithermal energy, you see that their response is worst in the energy range where we do not even have a reference field. So, Vincent, you're listening to this talk. I hope I brought the information correctly. The next gap we discussed might be created or is created by an approach to provide new quantities, new operational quantities for external radiation exposure. This is a proposal from the ICRU and ICRP. And this was also discussed due to the fact that this will mean an investment on metrology. This information is coming from Pete Burgess. He made an estimation for the UK that the costs to implement new operational quantities for radiation protection would account for roughly £1 million. For Germany, I could tell you it would be far more. PTB would have to renew all type approvals. Who's going to pay for that? And on the other hand, if we all pay for that, this will be an enormous amount of money invested in new quantities. Are we sure that the benefit is high enough? Pete even asked if there is benefit at all, but I will not discuss this point. We should be aware that the amount of money we can invest in radiation protection is not endless. If we spend the money in the quantities, we will not have much money left to improve radiation protection itself. So it would be interesting to know what CCRI is thinking about this and the quantities and the process to approve or not to approve them. Another long discussion was held for the aspects of the environment. This involves normally emergency actions and the communication strategies to the population. So we have some experience how to involve local population in the response, but this is not well established or harmonized. Here, Paul Leonard talked about the already existing experience, and we had also some support from the agency, from Rodolfo Cruz Suarez, and he added some further point to these questions. How can we do the dose assessment? This has to be done in a combination of bioassay, biodosimetry, different methods, and should this also include retrospective dosimetry methods? We are not prepared to have harmonized methodologies about this. In case of field monitoring, you must understand how environmental monitoring works under normal conditions. We are close to the limit of detection, and the networks providing environmental dose rates are designed to measure low-level radiation. But in case of an accident, of the passing of a radioactive plume, something like this, the activity concentration deposited on the surfaces will create a high dose rate peak. Are we prepared to be able to measure this in the time resolution we need? Are we prepared to see the nuclide vector? Do we have spectrometry installed or simply counters? And final point here for the environmental monitoring was also the emergency measurements and the natural occurring radionuclide measurements, which are of course always in our signal when we do our measurements in the environment. So you see here some needs, but we can also provide some examples about starting of solutions. So in the moment, there are several projects worldwide to use scintillation detectors on drones, for example. You see here on top a drone equipped with cesium bromide detector able to carry out measurements on the surface unmanned, and this means that you have bring nobody to harm by passing over a contamination area. This works pretty fine with photons, with gamma radiation, but how about the alphas? We all know that measuring alphas means to go very near the source, few centimeters. But there is a new approach, and this is the remote and real-time optical detection of alpha-emitting radionuclides. This is a process how we could measure alpha emitters from several meters, from the height of 20 meters, 30 meters, depending on the activity. And if you're interested in this project, please contact Faton Krasniqi and learn more how we get rid of this still big problem of measuring alpha contaminations, hopefully. The next issue I would like to address is quite directly related to radon. We had a large discussion on radon, and I think this is motivated from the fact that radon is dominating the natural exposure to radiation. In the moment, we have a limited number of suppliers of primary radon gas standards. And here we come back to our role of metrology. We have to supply the standards that our stakeholders, that you are needing. And we have to understand what you need. Therefore, it is important that we talk to each other. There are only very few facilities and NMI which are providing activity concentration, and in the moment we have only one lab that provides proficiency testing of radon monitors. Is this enough? If we consider that radon is dominating the natural contribution to the exposure? Another problem, oh, by the way, this was presented by Stefan Feige from BFS. The next problem, if we get access to the activity concentration or the exposure to radon, is how can we convert this to a dose? In radiation protection, we are thinking in form of a dose, not of activity concentration or exposure. In case of that, we have to harmonize the way how we convert the exposure to a dose. But in the moment, this is not done. The amount of dose in correlation with activity concentration changes from one border to another. And there we have a clear harmonization need in Europe, but probably we have it worldwide. Then I would come to the activity standards. You are probably well aware there that we have a quite large number of activity standards available, but not always for the needs of radiation protection. In nuclear medicine, we have new nuclides. We also need nuclear data with small uncertainties, which are internationally accepted. We have the need of special shapes and materials of our activity standards, mainly for the use in medical application. And we come to the point that we not only need activity standards, but also reference materials and reference analysis tests and comparisons for already implemented methods and for new methods. Here the examples were radiometric measurements and mass spectrometry. And then, of course, there's the ongoing discussion on computer-based tools. We have it since many years. A long time ago, when we implemented Monte Carlo simulation as a basic tool also in gamma spectrometry, we were able to cover this and discuss the outcome in the scope of uncertainty also. Now we have a new revolution at the door. This is methods from artificial intelligence. And how shall we get access to their uncertainties if we apply them, for example, in gamma spectrometry? This is a very new and interesting field where technology shows us new ways, but also present new challenges. So this was presented in the workshop by Stefan Röttger. And now I come to a final gap, and this is very closely linked to metrology. For us in the metrological community, uncertainties are at the core of our work. But if you have a look from the side of radiation protection, there you have the concept of a limit. And the main question you're asked in the scope of a regulation is this limit kept? And how do we implement uncertainty in this concept? You see a picture to the right side, and I would like to ask you, at which kind of measurement is the limit kept? In the scope of the uncertainty or not? And if you bring the concept of uncertainty to the concept of radiation protection, then we run into the problem that usually in radiation protection, the uncertainties are very, very large. So it will be difficult to keep the limit if we bring into the uncertainties. There are two ways to solve the problem. On the one hand side, we can drop the concept of uncertainty for radiation protection. And I'm not feeling very well about this as coming from the metrology community. Or we should reduce our uncertainties in radiation protection. And this is clearly a thing to do. This was presented by Takatoshi Hattori during the workshop. And of course, we have a lot of activity running for standards, and this was presented also in the discussion. Standard work is an enormous amount of work. Here you see a collection on different standards produced in the moment at the IEC, and still we have a lot of harmonization need here. And I would like to remind you that in case that we change our operational quantities, we have to renew a lot of standards. And this is an enormous work to be done. This was presented by Rolf Behrens. So we have gone through a lot of gaps, and now you might ask, there's so much work to do. What could be the solution? One solution that was proposed by Euromet is to join forces in our regional metrology organization, that is Euromet, to bring people together and to form networks, to be able to cover gaps and to provide new solutions for the requests of our technology. And you see here a picture from the Euromet's presentation, and you observe that there are already some European metrology networks established for mathematics, lab medicine, quantum technology, smart grids, energy gases, climate and ocean observation. And I'm here to propose that we need one for radiation protection as well. With all these gaps behind us and the knowledge that we have the need for the metrology here, that we have to bring the metrology to the stakeholder, as Stephen explained in the beginning, I see a clear need to have a European network for radiation protection. And this could provide a solution to solve the issue of a lot of duplication and create new infrastructure to solve the problem of our gaps as presented before. So what does this really mean? Where are the stakeholders in Europe? You probably know that in Europe, our European Union was formed from a lot of treaties, but one is still existing, and this is the European Atomic Energy Community. So this still exists parallel to the European Union with the member states, as you see here, and its regulation are the Council Directive of Euratom and the treaty that originally in 1957 established the European Atomic Energy Community. So the idea of an EMN for radiation protection could be to provide metrology support for radiation protection here in the scope of this regulation, to provide the quality infrastructure to support the regulation in Europe. So here you see some part of a regulation, the Council Directive, and we know that the regulation is changing in time according to the needs. So thinking about the need of surveillance of workplaces, individual monitoring, environmental monitoring, and public dose estimation, we get our rules from the regulation. And as the politics want to make a world better, they are lowering the limits more and more, and we have to react on the metrology part. And if we were able to implement such a metrology network, we could do this more efficiently, but we could also provide a feedback for the regulation and explain what is possible in the scope of radiation protection and where we do have research needs, or where it's simply not possible to fulfill the request of regulation. So this could be a very good motivation. And here you see a little bit of the history of the project, which name is Support BSS, which started in June 2020. So it's a pretty new project, but it has quite a long tradition. So the topic itself was proposed in the beginning of 2019. So the European networks will form a third pillar under the roof of Euromet, and our aim is to be one of the metrology networks. We submitted our proposal. This was approved, and now we have a little bit of funding under the Ampere call to bring together the people and to start the discussion on the metrology for radiation protection. Our aim is to provide a proposal in February 2021 and to go to the GE of Euromet with this proposal. And we hope it might be improved. This is the outline of the project, and you will realize that you already know some of the pictures and, of course, the covering layout of the background. So the aim is to provide first a dialogue between metrology community and the stakeholders. As I expressed, this is very important to understand the needs. In the network, we also want to provide a web-based platform, so everybody has a single point of access to understand where he can find solution for his metrology need or his calibration need or his question. And we will need strategic research agendas for the Euratom Directive and the Euratom Treaty research needs. We will also try to make first knowledge sharing and capacity building activities in Europe, and I could already invite you to follow the project and to benefit from these activities if you are interested in it. And in the long run, we hope that by understanding the needs, by understanding the gaps, and by understanding the duplication of metrological capacities, we will be able to provide a joint and sustainable European metrology infrastructure for all kinds of questions for radiation protection. So this is far too much to read, but the most important word is written in bold, and this is the final objective is the LARA principle, as low as reasonable achievable, and therefore we need the support of radiation protection metrology. And this is written here for every European citizen, but I hope you agree that this would be much better if we see it on a worldwide level. So the objectives of the project I already mentioned. The stakeholder involvement is at the core. The web-based platform to combine the capacity and the stakeholders to bring everybody together, to develop the strategic research agenda, and to set up a knowledge sharing program for stakeholders, not only in Europe, but to bring our questions and our answers to everybody who is interested. And the final aim will be a joint sustainable European metrology infrastructure. So we had a kickoff meeting, and when you look at the different work packages, you see here that the stakeholder needs are at the core of every work package. So this is a network designed for the support of all people who apply radiation protection. And therefore we need the discussion with you. The meaning of an European metrology network is to bring NMADIs together with the stakeholder. And this means, are you interested? Here is the EMN, and it should work, it should help to bring the worlds together. When we proposed this project, I asked many of you for a letter of support. and I would like to read what the agency wrote about the project. And I think this is really good motivation to keep on, even if it's a long way to go. The project objective and scope are of vital importance for the implementation, not only for the EU directives, but also for the International Atomic Energy Agency basic safety standards. So this is also my motivation to give the talk today to you, to give it worldwide, to give you the information, to ask for your feedback, and to offer you to join in when we form here our proposal for an EMN. The proposer is in the moment myself. The supporting delegate will be Jörn Stenger, and we want to go to the Euromet GA in 2021. So we already started to write the papers and to organize the work. And this is not so easy. We have a large amount of paper to produce and to get things ordered. So in our roadmap of the EMN for submission in February, we will have the proposal ready and checked by the NMIs latest in January. We wrote the proposal and the memorandum of understanding in a draft form, which is now with the partners. And the first draft was written in September. And if you are interested to be a part of the proposal, then please contact me. We started this in June, so it's not so easy to get every information worldwide communicated, but I'm grateful to Stephen that he gave me the opportunity to do it now. So you see our route, you see the aims of radiation protection. And as a final transparency, I would like to show you another point. Not only that radiation protection is at the core of what we are doing, but also that this is a powerful tool that our knowledge of ionizing radiation can help completely different communities to work better and more efficient in metrology. And this is what I called a new vision. We talked a lot about radon already, and if you think about radon and you're coming from a radiation protection community, you will think about it as something to be cared of, to protect. But it's also a very valuable tracer in climate observation. With radon, greenhouse gas flux measurements can be performed using radon as a tracer with the activity concentration and the radon flux measurement from the ground. And I think the most convincing picture is this one. You see here, in correlation, the concentration of methane, the concentration of carbon dioxide, and the concentration of radon in air. And this is the reason why large networks like the Carbon Portal and the ICOS network, the atmospheric station specifications state that radon is a very valuable tracer for the estimates of the greenhouse gases to determine source terms of greenhouse gases. So this is a network which is using to some parts the radon tracer method already. And you see here that this community can also benefit from our capabilities in measuring the activity concentration of radon and radon flux. And now I'm really at the end of the talk. If you're interested in this specific project, you can contact me as well. And I would like to thank you for your attention, for joining this workshop. I would like to thank once again the BIPM to give me the opportunity, all my colleagues involved in the Support BSS project, and of course, I would like to thank all of you for joining this talk. Thanks.